Hello, do you know that hot gases emit light with discrete line spectrum? What do I mean by that? Now, most hot objects emit light with a continuous spectrum. It could be the hot tungsten filament, it could be a candle flame, it could be the sunlight. They all have a continuous spectrum, from the reddest red to the bluest blue. The light given off by hot gases, however, show a discrete line spectrum. It's not a continuous spectrum, but it's also not monochromatic, because each line shows a wavelength. This means the light given off consists of light of this wavelength, and this wavelength, this wavelength, and so on. The reason why hot gases emit light at specific wavelengths is because gas atoms have discrete energy levels. And when the gas atoms de-excite, they give off photons whose energy correspond to the energy gaps. It may be clearer if I show you this equation here. So the energy of the photon must correspond to the energy gap. And since the energy gaps are constrained by the discrete energy levels that the atom can have, the atoms can only emit light of specific wavelengths. So how can we excite an atom before they de-excite to give us the photons? The easiest way is to bombard them with electrons. Let's say we have an atom with these discrete energy levels and is hit by this electron with Ke of 1.0 electron volts. So let's make it clear, this represents an electron that's trapped in the atom, whereas this is a free electron enjoying its freedom outside the atom. So can this electron excite this atom? No, it will just pass right through it. Because the atom is currently at negative 3.5, and even the smallest jump to negative 1.5 requires energy of 2.0 electron volt. This electron has only 1 electron volt of Ke. This amount of energy cannot be absorbed by the atom because that will only bring it from negative 3.5 to negative 2.5. But negative 2.5 electron volts is not one of the allowed discrete energy levels. So we need the bombarding electrons to be more energetic. So let's say 2.1 electron volt. Now it's possible to excite the atom to go from n equals to 1 to n equals to 2 after it absorbs 2 electron volts of energy from this electron. So this electron will keep 0.1 electron volts of Ke. This is called a scattered electron. Now the atom is at n equals 2, so when it de-excites, it will emit a photon of energy 2.0 electron volts. What if the bombarding electron has Ke of 2.8 electron volts? So this is sufficient to excite the atom to go from n equals to 1 to n equals to 2, and the scattered electron retains 0.8 electron volts of Ke. When it de-excites, of course, we get a photon of 2.0 electron volts. But this is not the only possible interaction. It's also possible that the atom absorbs 2.5 electron volts of energy to go from n equals to 1 to n equals to 3. If this happens, the scattered electron will retain only 0.3 electron volts of Ke. Now the atom is at n equals to 3. This makes 3 down transitions possible, which means 3 possible photon energies. If it de-excites from n equals to 3 to n equals to 1 in one big step, then we get a 2.5 electron volt photon. But if it de-excites in 2 steps, n equals to 3 to n equals to 2, followed by n equals to 2 to n equals to 1, then you get 2 photons of energies 0.5 electron volt and 2.0 electron volts. So with 3 energy levels, it's possible to get 3 photon energies and thus 3 emission lines. If you want more emission lines, you have to excite the atom to even higher energy levels, like n equals to 4. So for example, if the atom is hit by an electron with 3.0 electron volts of Ke, then it's possible that the atom absorbs 2.7 electron volts, leaving the scattered electron with 0.3 electron volts of Ke. Now from n equals to 4, you can have 6 different down transitions, resulting in 6 different photon energies, because you can de-excite in one big jump, or in 3 small jumps, or in 2 jumps, this and this, or this and this. So you see, with 2 energy levels, you get 1 emission line. With 3 energy levels, you get 2 plus 1 emission lines. With 4 energy levels, you get 3 plus 2 plus 1 emission line. So how many emission lines do we get if we have n energy levels? It'll be 1 plus 2 plus 3 all the way until n minus 1, right? Another way of saying 1 plus 2 plus 3 all the way to n minus 1 is simply n choose 2, which makes sense, right? Why are there 6 emission lines here? Because we're always choosing 2 energy levels out of 4 energy levels to make the down transition, and 4 choose 2 is 6. Okay, one last one. What if the atom is hit by an electron with Ke of 4.0 electron volt? In this case, there's sufficient energy to knock the electron right out of the atom. So this electron, which used to be bound in the atom, is now completely free of the atom. Since it's outside the atom, it's not constrained by any discrete energy level structure of the atom. So it can escape with Ke of anything ranging from 0 to 0.5 electron volts. So correspondingly, the scattered electron can also have a range of energy. The ground state energy level is also called the ionization energy. Because that's the energy required to throw an electron out of the atom, that's the energy required to ionize the atom. Alright, that's all. Ta-ta!